So I've been a little bit busy over the weekend, participating in several contests. I kind of wanted to do some analysis, post-contest analysis, but before that, I wanted to actually upsolve all the problems from all the contests. And I still have two to go. One is problem H from AtCoder beginner contest, and another one is problem F from Codeforce's Div 2 round. So I guess this one will be coming a little bit later, after we take a look at some AtCoder problems. They are called AtCoder beginner contests, right? But keep in mind that that is a very vague term, so some of these problems may be not that beginner friendly. I still hope they are like easier than certain Codeforce's expert problems. I'm not 100% sure that they are like actually suited for absolute beginners. So I'm assuming that you kind of have some experience with competitive programming. We'll talk more about what kind of experience is expected to solve such problems as we go along. So the first one is, it comes from, I don't know when, from AtCoder beginner contests 210, which I suppose was around like 2 months ago. Yeah, and I did not, funnily enough, I did not solve this problem during the contest, despite it being only D. I was like, I strongly disagreed with this problem being labeled D, because usually ABC problem D was much easier at that time. And it is kind of easy, but only if you get the right idea, and I did not get the right idea during the contest. I was thinking something completely unrelated to what was expected, unfortunately. But when you do get the right idea, it's fairly easy. So in this problem, we have a grid of H rows and W columns, so a grid like that. It represents certain cities, let's say, of some kingdom. The king of this kingdom, they want to build a railway. A railway will connect two cells of the grid. Let's actually take a look at this example. Here we can build a railway from here. Oh no, that's not nearly enough this size. Okay, so we'll do a grid then. Alright, fine. So in this grid we kind of connect two cities by a railway. So railway, you know, like how railways work. You have a station, you have some rail track, and then another station. So this problem tells us that we do have to spend money for building a station at every cell, and that's what this cost matrix is all about. So there is a cost to build a railway station at every grid cell. Now, after we build two stations, we only want to build two and connect them by rail. So after we build two, let's say we picked this one, and we connect them by rail. And this rail costs very interesting cost to that. So let's say that this row is row I. Do they have some? No, they just have I prime, J prime. Okay, this row is numbered I. Rows are of course numbered from 1 to like horizontal, I assume. Columns are numbered 1 to 1 to height and 1 to width. So the first row is I, the second row is I prime. First column is J, second column is J prime, and you have to pay the Manhattan distance between them. So like this distance plus this distance times some fixed cost. Now, unfortunately, what I did not realize during the contest is that I'm supposed to visualize that. I was thinking about really like abstractly, that we can just connect to vertices and that's it. What I was expected to think of, I believe, is the following. So the railway, it's not like, it does not go like this. The railway, it is just perpendicular to the sides. So like we build two stations, and our railway, we can always say that, well, that's kind of like a grid path on it. But unfortunately, I did not think about it during the contest. Very unfortunate, and that's why I strongly disagreed with this problem being D. Because like without this idea, you have no chance of solving the problem whatsoever. That is a tricky thing in some of the beginner problems. They may require only one idea, but without it you may be stuck forever, which is very unfortunate. So the only way around it, I believe, is to just like, you see, the more problems you solve, the more ideas you see, and generally speaking, the set of possible ideas is not that huge. But I still think it's not D. It's more like E. But maybe I did not solve enough AtCoder beginner contest to make such claims, but that is just my personal opinion. So don't judge me too strictly on that. But the point is, like, you can think about your rail as being physically going horizontal, vertical, stuff like that. Why is this important? Because with this kind of rail system, your problem somewhat transposes into DP with the following idea in mind. Suppose we want to get, like, suppose that one of the endpoints is actually this number 4 here. So this cell is one of the endpoints. How we can compute then, like, the answer for this cell? What's the minimum cost of the railway? Well, how goes the railway? You may have came from you, like, surely you can't build two stations in the same place, so you came either from here or from here, right? Each of these corresponds to a cost of C. So each such transition has a cost of C. But you don't need to start here. You may have started somewhere before. So like, so now our objective transposed into getting here or here with minimal cost. So we have three options how to get here with minimal cost. Well, first we either started here, that may be beneficial because we don't use any rail. Second option is we came from the left somewhere and then we get the recursive problem. Third option is we came from the top. So like, what's our, you can see some recursive structure, and here usually dynamic programming helps. So I'm assuming that you know something about dynamic programming. We'll get back to the right moments. So our idea is to have the following dynamic programming. Let me draw a separate grid for that. Maybe it will be better if I draw them underneath each other. Now our problem transforms to what's the minimum cost to get to the cell from somewhere left or up. Notice how I said that we all only want to build rail in such directions. You may disagree, like, what if the best pair is like 3 and 8 this way? And then we surely have to build left. That's absolutely true. Or you may want to build something like that or that. It is true. But without too much losses or generality, we may assume that optimal pair is located like that. So one is somewhere is left and top, and the other one is right and bottom. Why? Because other pass spotted this is optimal. We'll do two things. We'll process the initial grid, and we also process the reverse of it. So that should cover all paths. That's one more important trick, is like if you want to fix the configuration and there are not too many of them, you can just do that and then like loop over all possible configurations later on. Another way it may come up is like when you make, let's say, you need to make a scan. You may assume that you're making a vertical scan top to bottom, and then you will do this scan, and this scan later. Like there are only 4 of them, so that's not a big deal to assume that you're dealing with one situation. If you can solve one specific case quickly enough, and you will be able to solve 4 with not too much overhead, right? So if you can benefit a lot from fixing the configuration a little bit, do it. But here we are solving the problem of what's the minimum cost of getting to certain position from somewhere to the left and above it. So like here, we'll also use this value of 2, which does not have costly one piece of rail is. What's the minimum cost of getting to 1? You can't exactly go from here or here because there's nothing. So your cost is just 1. What's here? You can't go from here. If you start here, the cost will be 7, but you may come from the left, in which case cost will be just 3, which is surely better. Just keep going from the left. Here we think, like, oh, well, obviously the cheapest way is to get from above. Here it's 5, but here the cheapest way is to start here, and here the cheapest way is to come from here. So here the answer is 5. Here from above, here does not matter, just don't start here. Here the minimum cost is 5 of getting from above. Here just once again it's the cost is 4. But keep in mind, like what we've done so far, we built a first station somewhere, and then we've taken some rail. We are yet to build the second station, the closing one. Excuse me for a second. As you can probably tell, I'm not particularly healthy at the moment, but let's hope it does not affect my voice and stuff like that too much. So the video still stays legit. So now we have to build the second station somewhere, and we can just say, like, if we build a station here, like our source station is either here or here. Well, not necessarily there or there specifically, but more like in this rectangle. Therefore, we may just consider the last piece of road, like how did we came to this cell specifically. And it was either from above or from the left. These values, I remind you, they do not contain the cost of starting here and going somewhere. It's like the cheapest you can way to get to this cell from somewhere in this rectangle. So that's doing exactly what we need. Like we just consider what was the last piece of road. We either come from here and this cell contains the information about the cheapest route here, or we come from here and this cell contains the information about the cheapest route here. So overall we cover the entirety of this rectangular sink. That's how we do it. Let's take a short break and take a look at the implementation straight afterwards. So we are right back. We'll take a look at the implementation section as we usually do. I constantly forget that I have to close it. The implementation itself is fairly short. Like this part, we are just reading the input. Then we will have a function scan, which does this sync. It scans from left top to right bottom. And then we'll call it once, and we'll reverse the array. Now that I said that we'll reverse this way, we actually reverse this way, which also works. Because once you reverse this way, such paths, they become such paths. And such paths are exactly what we scan for. That's all good. Here the scan works as follows. I want to compute the second matrix, remember? Because it's then immediately used to compute the answer. Now it's a little bit nicer if I pad it with like infinite values. For infinite values I use something really large, but not too large for it not to overflow. Because if you add in a value like that, plus c, you may overflow if the infinity was set to that. So that's why you really want to make it very large, but make sure that it does not overflow after the operations. So I give myself a little bit extra padding here of like positive infinity values. Because remember, when we are trying to minimize something and you need the sentinel value, you should pick a maximum, a positive infinity, because minimum of positive infinity in any value x is just x. That's kind of a property for a neutral element that you want to hold. So that's how we decide that we want positive infinity here and not negative, let's say. And then we just have our loops, as I said, like this matrix is computed in a DP fashion. We look up at every cell. We either start here, we look left, or we look up. That's what these are about. And then they are looking for like, what if the current cell is the endpoint? Then we either come somewhere from above, then we have to build one piece of road and build the station right here. Or we are coming from the left, we have to build one piece of road and build the second station. So yeah, implementation side, this is a really simple problem. Idea-wise, not so sure. That's why this episode has a question mark in the title, because these problems are like not particularly highly rated on Kenku.com. Just in case you don't know this awesome resource, let me show it to you, because that really helps a lot with practice on AtCoder. So worth saving to your bookmarks. It has like all problems that you ever solved. If you solve it in contest, it also has a time. If you had some wrong submission, it also remembers this. If you upsolve it, it's a different color. So like a lot of stats here going on. You may like there is also AtCoder regular contest and stuff like that. There are a lot of user-wise stats that you can see somewhere here. Something here was like very interesting. Oh, I guess this one shows like how many problems you solved over time, and also of which difficulty. So we can see that I solved a lot of very simple problems, and then like harder ones, they take like 10% of what I was solving. But it will be the case with like it's natural behavior. We see that I was kind of active in July, not so active right now, but maybe that's going to change soon. But yeah, really nice. It also has recommendation sections, which like for easy, moderate, difficult, you can probably guess the difference by the color. It also has like rating estimates for all problems. This is something Codeforces does towards the nearest hundreds automatically. On AtCoder, it's like external resource, but yeah, that's kind of really widely used. So I guess the estimates are legit. Also shows like median solve time, which is crazy for this problem, and also solve probability. Oh, the median solve time must be crazy because that's like ACPC style. Not so sure about that. Anyway, it was only one of the 3 problems that I wanted to share with you today. The other 2 are like, well, this one is somewhat easier. The other one is somewhat harder. So let's take a look. In this problem, it's more like formal, not so much description to it. We are just given it 2 integer sequences of lengths n bars, a and b. And we want to count subsets of 1 through n, such that maximum of ai's selected is greater or equal to the sum of selected bi's. And of course, we want to mod it. N is not particularly large, which like the first idea here is to maybe have something quadratic. Not so ai's and bi's are not large. If you done some competitive programming or interview prep, then this part, the right hand side, should be fairly familiar to you. Because what is actually saying is we want subset sum to be at most something. And surely you are familiar with subset sums and how to compute them using dynamic programming, which is exactly why values are not particularly large for the sum to be limited. Actually, the limit for the sum is maximum AI, so you can compute subset sums reasonably quickly. So if we are able to get rid of maximum in any way, that will mean problem solved. Because subset sums is a well-known problem that I expect you to know about it. If you don't, then you probably can just look it up. So how to get rid of the maximum? A normal, standard technique in such a case is we say, okay, let's say that maximum of our AIs will be some AJ. All right? Like we think maximum is a 9. We want to know it. We want it not to be a variable. So we say like, okay, AJ will be the largest element that we select in our subset. How we can guarantee that? It means that all other elements, they are like subset of values that are smaller or equal to AJ. And all other elements that are greater or equal to AJ, we don't take them. We don't take them. That is a no. But that's all fine. So it makes it natural, very natural, to sort pairs, and I want to highlight that we want to sort pairs because the indices are linked, of course. So we sort pairs AI, BI in increasing order of AI. Once we've done it, we want to say like we want all subsets up to J, up to certain index of B with sum at most AJ. So what we say is like we do take AJ, then we do take BJ, that is important, and we were interested in how many subsets are here such that we take some of them, we take this subset, we add this all together, and it's at most AJ. And this is easy to recompute after, like, suppose that you know this information here. How many subsets give which sum? It's very easy to recompute it when you add another element in of m time, where m is like maximum sums that you are interested in, which is maximum AI, so only 5,000. So the overall complexity will be of n m, because we add one element n times and then we do of m work per each addition. It's like how you compute your subset sums, right? But at each iteration, you want also to scan the map and answer a question how many values there are up to AJ. So that's what we are going to do here. Yeah, but these two observations I got fairly quickly. It is actually comes from ABC 216, which is a contest that I unfortunately missed. So that's a shame that I did not participate here, because compared to the previous one, this one I got really quickly. So let's take a look at the implementation. It may be clearer what I mean by subset sums and stuff like that when we take a look. So we do read our ABs, we do compute maximum of A as we go. We sort our ABs. They naturally get sorted by A component. Then we have our subset sums. So this vector will tell us, the i's entry will tell us how many subsets have sum of exactly I. What we do next is we loop our ABs. We say, I do take A, alright? And I also do take B, and I want to know how many subsets there are, so that their sum plus B is at most A. So what it means that their sum is at most A minus B. So we just count this, add mods, everything. Oh, I got a unpretty tab here, unfortunately. I hope that's not a huge problem for you. That counts, that for loop counts how many subsets are good. Now the loop that updates the counts of subsets is this loop. And hopefully you know that in subset sums, if you would only have one occurrence of each element, you should go in reverse. So we loop over all possible sums from M to B, and we say like, if we ignore element B, then this count stays the same. So that's why we should plus equal and not a sign. So we can either ignore, which corresponds to this part, or we can take an element of B and add it to any subset with sum J minus B, and that's why we plus equals this this count of this is how many subsets there are with sum J minus B, and then we add an element with value B, so the subset sum will become J. And we do it in reverse because we only have one occurrence of each element. If you do it forward, you may notice that when you add very first element, let's say it's 2, then if you do it forward, then all your even entries will have one subset. But that's technically not true, because we are reusing the same value of b over and over again. If you do it this way, we always take a look at the smaller value that has not taken b yet. That's why you want to go in reverse when you have one occurrence of each element. That's it. Once again, very short implementation, but I imagine it can be quite tricky if you don't get the tricks, right? So that's why it's important to take a look on different problems on different platforms, because they usually mean that you are exposed to a wider variety of problems and ideas that can help you solve more problems, right? So it's like, it must sound obvious, but it was not obvious to me like for a long time. I only started doing other than Code Forces and Code Chef this year, like 2020 and prior. I only did Code Forces and very occasional Code Chef. Only in 2021 I started doing AtCoder, AtCoder. Well, I was doing LeetCode in 2020, but I don't really consider it like a competitive programming website. BinarySearch.com only in 2021. HackerEarth, I did one contest in 2020, so like prior to 2020 I was only doing Code Forces and Code Chef very occasionally. In 2020 I did some LeetCode in one contest on HackerEarth, but only in 2021 I started using AtCoder, AtCoder, BinarySearch.com. What other things around? Well, you can probably check my clist.by page if you're interested in that kind of stats. But I can tell that it greatly helps to get some exposure to different thinking schools, I would say, because AtCoder problems are surely different to that of Code Forces in spirit. Despite sometimes the problem setters may be the same, but problems are still different. So yeah, let's take a look at the last problem, which I also did not solve in contest. That is actually comes from the same contest as our first problem, but that's problem E. So like when problem D a little bit freaked me out during the contest, and problem E came, and it was just like a complete disaster. Actually, because of these two problems, I stopped doing AtCoder for like 2 weeks before I could get back on, because I had no idea what I'm supposed to do in this problem. Apparently it's not hard. But once again, like, it was just very unfortunate that some contest featured 2 problems in the middle of it, which like you can't solve if you don't get the right idea. It's not like you get a worse solution, not that nice to implement. It was like you get no solution, which was very unfortunate. But yeah, today I came back to it and it was actually easier. So like, it does help when you're practicing, let's say. You're not in a contest, you can come back to a problem later. It does help. Like for D, I actually had to look up the editorial to get the right idea. For this one, I more or less solved it on my own. I just had to come back to it like later to get the right idea. So maybe taking breaks helps even during contests, but I'm not so sure about that because you're like obviously wasting time. But if you're solving problems for practice, you may want to consider like just coming back to it tomorrow instead of like looking up the editorial or asking random people on the internet, because you certainly get more value out of the problem if you solve it yourself. And this problem we have a graph with n vertices labeled 0 through n minus 1, so like remainders modulo n. And at the cost of ci n, we can connect two vertices that differ by ai modulo n. I want to find the cheapest way of connecting them all together. Or tell it it's impossible. So here, what I recognized is like, well, as the problem says, we are getting a minimum span tree of this graph. We may say that we draw all edges, each edge has some cost, and then we want to find the minimum span tree. Now the way minimum span tree works in specific Kruskal algorithm for file needs is that you want to prioritize cheapest edges first. So that is something I forgot about during the contest. But once you remember it, it becomes much easier. So once again, like, because we want to prioritize cheapest edges first, and you can look up the Kruskal algorithm for minimum span tree if you want to. But it sounds natural that you want to prioritize cheapest edges. So we can sort these pairs based on the value of C. And once we do it, we basically want to add each edge that connects to disconnected vertices. Now you want to understand like how much you can connect in one go. So let's take a look at some example. Like here we have 4 vertices. At the cost of 3, we can connect any, any 2 vertices that differ by 2. At the cost of 5, we may connect any 2 vertices that differ by 3. So naturally, like you want to connect this and this at the cost of 3 each, and connect the remaining ones at the cost of 5. Just to clarify, this edge of length 3, it may actually be this because it's modular. So like 2 plus 3, but modulo 4 is 1. You may actually add such an edge. You may add any edge, to be honest, but why would you do it? And here what you notice is that like if your edge length is co-prime with your modulo, then you just connect everyone together. So that's very, very nice. What is not nice is when your edge length is not co-prime with the modulo. So here, for example, edge length is 2 and n is 4. So you can't connect even and odd numbers together, despite looping over the modulo. So like 2 plus 2 will get you back to 0, so not very helpful. What is helpful, however, is that if it does not connect everything, then it connects everything into equally sized components. So like all even numbers, there are equally many even and odd numbers. So you had n numbers, then you basically, and you have some AI, right? Well, if n is divisible by AI, then you can just divide. Otherwise, you need to take a GCD of n, greatest common divisor of n and AI, and that is how many components you are getting. All of them will be of the same size. So now you can like ignore them and change them to one vertex. And by knowing how many components you had before, so like I had n components before, I now have g components. It means that I used n minus g edges to connect them up, right? Well, of course, I also need to change n after this operation because I said like I'm interchanging everything into every component into one vertex. So what happens is that I draws that many edges of cost ci each that reduce the number of vertices from n to g. And then I repeat the process, and I do that in increasing order of ci. So that's like implicitly carrying out the Kruskal algorithm, but also saving a lot on like not drawing edges, but just counting them. Because your graph is always like very symmetric. All components are of the same size. That's it. And you don't, and it works because like after this, if you may say like, wait a second, like if I get 3 large components, taking a step of 2 is no longer the same as taking a step of 2 maybe like here. That is technically incorrect. Because, well, this is technically correct, but we don't care. Because still, like we are getting into a different component with a step of 2. We are not getting like from a specific vertex to a specific vertex. If you treat these guys now as remainders modulus 3, then you still take a step of 2. It's just we don't care about specific vertices. Like it may have been like 6 vertices, so 0, 1, 2, 3, 4, 5. And our first edge length was 3. So we combine this and this, this and this, and this and this. Now we have 2 large vertices, 0, 3 actually, 1, 4, and 2, 5. Now our next step is 2, so technically we're going from 0 to 2, but we disregard the inner workings, and we just say we're going from this large vertex to this large vertex. So hopefully this example shows you why this process is even valid. Because after we compress a lot of vertices into one large vertex, the steps that are co-prime with what we had, they stay the same. So hopefully that like answered your questions or doubts if you had any. And we can look at the implementation, which is once again really short, but maybe very tricky to figure out. That's something I like about AtCoder. Like a lot of problems can be solved very shortly. It's very short code if you get the right idea. So it's like very idea oriented and not very implementation oriented. Whereas Codeforces is, in my opinion, much more about implementing things. Some time ago, like in a Div3 contest or something, like I solved all problems for the first time in a while, and I found all of them really standard from the idea side, but I still spent like an hour and a half implementing stuff. It could not happen in AtCoder. Like usually, implementation side is easy. So here we do read our CA. We would do it kind of cheeky because we want to sort by C. So I said like, okay, let's just put it first. Disregard the input order. So like A still gets read first and C gets read second, but they are laid out in memory differently. So yeah. Then we can sort just like this without specifying like comparator that we want to sort on. And we loop our CA, we keep a track of our like G or N. We could have reused our N variable for this actually. Which I did not think about it. But yeah. So we take with like compute next G, because we know that how many components we'll get after we apply this edge of length A. So we had G components, we have N G components, we added difference of edges. each costed us C. So we just multiply them together and add to our answer. Don't forget to convert to longs, because that may be long. And then we just update the value of G. One tricky thing is if G is, like, after you did all your updates, you have more than one component, then answer is impossible. So you have to check it. That's basically it for the implementation. Now with the problems out of the way, I maybe wanted to share some of philosophy behind this. So I do think that AtCoder beginner contests are somewhat easier than like Codeforce's Div 2, let's say. So you may want to take a look at them. I'm not exactly sure that ratings match up precisely, but it may be easier to start out here, where you don't necessarily need to care too much about simple implementation, and you are more like solving puzzles at the beginning. So yeah, just the following several days, like Tuesday, Wednesday, will still be on AtCoder. We'll gradually increase the difficulty, and we'll have 2 problems per video. But then on Thursday and Friday we'll come back to Codeforces, and that will be around master level problems. And if I ever upsolve the problems from the contests of this weekend, the past weekend, then I may want to make some analysis of these contests. So stay tuned for that. But other than that, I'll see you tomorrow with a new video, and I hope you learned something in this one. So yeah, bye bye guys.